Hello, welcome to the virtual ICM. I'm Ulrike Tillmann and I'm sharing this session from Oxford. So we are now going to hear a talk in the algebra section, which is also cross-listed as algebraic and complex geometry. And the speaker will be Neena Gupta. Neena got her PhD in 2011 under the supervision of Amartya Kumar Dutta from the Indian Statistical Institute. And after spending some time at Bombay, Neena returned to the Indian Statistical Institute in Calcutta and is there right now. In 2014, she received the Young Scientist Award by the Indian National Academy for the solution proposed to the Zariski Cancellation problem in positive characteristic. She also received just this year the Ramanujan Prize. So many congratulations to Neena for the prize, but also having been invited to give this talk at the ICM. So I give the floor now to Neena.
Thank you, Professor Tillmann, for this nice introduction. It's a matter of immense pride and pleasure for me to present this ICM talk. I wish this event could have happened offline and we could have met everybody personally, but thankfully I'm attending this event in Zurich, the sectional workshop. And so to have some feeling of the ICM, I will talk upon the Zariski's cancellation problem and some problems which are related to this. We first begin with a picture of Professor Zariski. He was born in Russia and he studied in the Italian School of Geometry and settled in America. He is known for bringing rigor in classical algebraic geometry and laying the foundation of modern algebraic geometry along with Professor Andrew Weil, and also connecting it with commutative algebra. Many important results in the 20th century are due to him. We begin with the cancellation problem of one of the version of the cancellation problem due to Zariski. For me, K will always denote a field, and A and K denotes the affine n space. It is a set Kn with a Zariski topology and the structure shift. And the cancellation problem of Zariski asks whether the affine n space A and K is cancellative as an affine variety. That is, suppose V is any affine variety and the product space V cross the affine line. Suppose it is isomorphic to the affine n plus 1 space. Does this necessarily imply that V is isomorphic to the affine n space? So what if over an algebraically closed field, this problem can also is equivalent to this following ring theoretic version. That is, whether the polynomial ring kxn up to xn is cancellative. That is, suppose A is any given ring and the polynomial ring in one variable over A is isomorphic to a polynomial ring in n plus 1 variables over the base field K. Does this necessarily imply that A is isomorphic to the polynomial ring in n variables over the field K? So note that the polynomial ring kxn up to xn plus 1. So this is a polynomial ring in n plus 1 variable. It can be expressed as a polynomial ring in xn plus 1 over this coefficient ring in infinitely many ways. For example, just look at the two variable case kxy. Then this ring can be written as a polynomial ring in y over the various subrings like kx, or you can take kx plus y or kx plus y square. So all these rings, subrings kx or kx plus y, they are not same, but they are all isomorphic to each other. The cancellation problem of Zariski basically asks whether all such coefficient rings are necessarily isomorphic to each other. So this will be my notation. For any ring R square bracket n will denote a polynomial ring in n variables over the ring R. Then the cancellation problem of Zariski asks whether the affine polynomial ring Kn is cancellative. This problem was known to have an affirmative answer for the affine line by Abhyankar, Ikin, and Heinzer. Actually, their result was much more general, and this case n equal to 1 was follows as a consequence of their much more general result. The case n equal to 2 was solved by Miyanishi and Sugi with an important contribution due to Fujita over a field of characteristic 0. And soon this result was generalized by Peter Russell over any perfect field. Along with Bhatwadekar, we have shown that the affine plane is cancellative over any arbitrary field. The proof of this result n equal to 2 was highly non-trivial. The research on this case had led to beautiful topological characterization of the affine plane due to C.P. Ramanujan and an algebraic characterization by Miyanishi. Eventually this algebraic characterization led to this proof that the affine plane is cancellative. Again, this topological characterization was also used to give an cancellation property of the K2 by Gurjar. So this is C.P. Ramanujan. Professor Mumford had said very nice words about him. He said that about him, he felt the spirit of mathematics demanded of him not merely routine developments, but the right theorems on any given topic. And these are the 4 stalwarts in the area of affine algebraic geometry: Professor Miyanishi, Professor Russell, Professor Koras, and Professor Gurjar. They have. So, however, after the solution of n equal to 2, the n equal to 3 case had remained open for long. And I have shown that over a field of positive characteristic, the affine n space is not necessarily cancellative. I had first proved it for n equal to 3 and later generalized it for higher dimensions. And this result for n greater than equal to 3 is still open when characteristic of the field is 0. Let me now come to the example how this result was achieved. So this is a ring due to Professor Asanuma. Here K is a field of positive characteristic P, and A is this ring, where this is the property of this ring. M is any integer. This ring was considered by Professor Asanuma in 1987 in the context of affine fibration problem, which I will be discussing. So it has been very crucial in, or I should say it was very important in deciding many important results in affine algebraic geometry. Say, for instance, Asanuma proved that this ring A is a stably polynomial ring. That is, after adjoining one variable to this ring, this becomes a polynomial ring in 4 variables. And this ring A is not a polynomial ring over the subring Kx. He again revisited this ring in 1994 in the context of linearization problem. And there he posed this problem, whether this ring A is a polynomial ring over the base field K. A major difficulty in the area of affine algebraic geometry is to decide how to show that a ring is a polynomial ring or not. So this is one of the most difficult part, that whether a ring is isomorphic to a polynomial ring. It was during one of his visits of Professor Asanuma to ISI. So Professor Asanuma had visited my institute, Indian Statistical Institute, and also TIFR several times. And it was during one of his visits that I was thinking about reading his papers and thinking about this cancellation problem, where I came across this example of Asanuma. This question of Asanuma had dual consequences. It was interesting consequences. That is, if you prove that this ring is a polynomial ring in 3 variables, then you construct an example that the linearization problem will have a counterexample in positive characteristic. On the other hand, if you prove that the ring A is not a polynomial ring, then clearly you have a counterexample to the cancellation problem of Zariski. And Peter Russell used to call this dichotomy as Asanuma's dilemma. I had shown that this ring of Asanuma, is not a polynomial ring whenever this integer m is greater than or equal to 2. So m is this integer. So if it is greater than or equal to 2, this ring A is not a polynomial ring. So there is still a chance that if for m equal to 1, this problem is not known. And if you can show that yes, for m equal to 1, this is a polynomial ring, then you may actually come across a counter example to the linearization problem. Now let me discuss what was the affine fibration problem, because in which Asanuma was considering this ring. So for any ring R and a prime ideal P of R, this notation K square bracket P, round bracket P, this will denote the field of fractions of the integral domain R mod P, and A tensor Kp is the fiber ring of A at P. So, so geometrically, it is the denotes the fiber of the ring R algebra A at the point P. A ring A is called an AN fibration or the affine fibration over R if A is flat over R, it is finitely generated over R, and all the fiber rings of A are polynomial rings in n variables over R. So this definition of affine fibration, there are in fact several other definitions, but this is the definition basically defined by Sathaye, and it has been very well popular. A famous problem of Dolgacham and Westphaler asks whether over a regular local ring of dimension D, any AN fibration is isomorphic to a polynomial ring in n variables over R. So this is a very natural question, and so if geometrically it means if all the fibers of the R algebra A is a polynomial ring in n variables or affine n space, and flatness gives you that regularity condition, does that necessarily imply that the ring A is a polynomial ring to start with? So for n equal to A1 fibration, any A1 fibration over any regular local ring of any dimension, it is going to be locally polynomial ring, and this was given by Kambayashi and Miyanishi. In a deep result due to Amartya-Kumar-Datta, my supervisor, he proved that this condition on all the fibers, you can reduce it to only prime ideals of height less than or equal to 1. So it is enough to assume the condition only on prime ideals of height less than or equal to 1. In a highly non-trivial work due to Sathaye in 1983, he proved that any A2 fibration over a discrete valuation ring which contains the field of rational numbers must be a polynomial ring. So this is highly non-trivial, and it requires the generalization of certain expansion techniques which were developed by Abhyankar. And his Professor Sathaye, he had been also visiting ISI several times, and my supervisor Amartya-Kumar-Datta along with me. So, and now this example of Asanuma shows that if the ring does not contain the field of rational numbers, then A2 fibration need not be a polynomial ring. So this is why this example of Asanuma is very important. This example of Asanuma had been generalized by me to give proof that example of A2 fibrations over any arbitrary ring of any dimension. However, if the ring contains the field of rational numbers, A2 fibration problem is a completely open problem. The best known result, or I should say the best known, at least some structure theorem, the result was given by Asanuma in the area of affine fibration. It says that over a regular local ring, any AN fibration is a stably polynomial ring. So in some sense, any AN fibrations are very similar, are the proper candidate for having counter example to the cancellation problem, because they are always stably polynomial ring. Now let me come back to this Asanuma ring again. So Asanuma's ring is of special type. You can see it's a linear polynomial in Y. plus a polynomial in G, Z and T. And this polynomial of G satisfies a special property, that is this G defines an affine line. That is, if you mod by G, then it's a polynomial ring in one variable, but G itself is not a coordinate in the polynomial ring KZT. For example, if you take G equal to Z, then Z is a coordinate and Z will satisfy this. But this polynomial G is, of course, not a coordinate. So it's not a coordinate. So this leads to this definition. A polynomial f is said to be a non-trivial line if it satisfies this, that is, it is a line, but it is not a coordinate. And examples of non-trivial lines were given as early as in 1956 by Segre, and a family of examples were given by Nagata in 1972 over the fields of positive characteristics. So it was known that there are polynomials which defines a line but which are not coordinate. What if characteristic of the field is 0? So this leads to this theorem of Bhatwadekar. He is one of the most illustrious student of Zariski and founder of affine algebraic geometry. He has greatest contributions in many areas, including the resolution of singularities and inverse Galois theory and so on. Our Indian school had inherited a lot, means in developing a branch of affine algebraic geometry in India, and I was probably one of the beneficiary of his teachings or his inspiring. So this was this theorem of one of this landmark theorem of Bhatwadekar and Moe, that if K is a field of characteristic 0 and F and G are two polynomials in one variable, such that you can get T from F and G. That is, there exists a polynomial in two variables, and if you plug in F and G in that, then you get T. Then either the T degree of F must divide the T degree of G, or the T degree of G must divide the T degree of F. So this was highly remarkable, and this implies that whenever F is a polynomial in two variables, defines a line, then F must be a coordinate. That is, over a field of characteristic 0, there does not exist any non-trivial line. And this was also proved independently by Suzuki over the field of complex numbers. Again, so a major difficulty in the area of affine algebraic geometry is to decide when is a given polynomial f a coordinate. So this for two variables is probably one can decide by using the automorphism structure of KZT, but if for n greater than 2, so for any polynomial ring in n variables, it's very difficult to decide whether f is a coordinate. And this leads to this Bhatwadekar-Sathaye's conjecture that over a field of characteristic 0, whenever f defines an affine n-1 space, then f must be a coordinate. So this is a conjecture, and it's open. And so the n equal to 2 case was due to Bhatwadekar-Moe and independently by Suzuki. So for n equal to 3, some special cases have been taken care of, like this result of Sathaye and Russell. So here he considered G to be a linear polynomial in Y. Then they have proved independently that Sathaye had proved it for characteristic 0 and Russell generalized it to arbitrary characteristic, that you can find an coordinate x1 in x and z such that this coefficient of y is a polynomial in just one variable, and G is a coordinate along with x1. So we can generalize this question in 4 variables and ask, what if G is of this form and G defines an affine 3 space? Does this necessarily imply that G is a coordinate along with X? So the answer is yes. In the special case, I considered it for the case when AX is x to the power m and m is an integer greater than 1. This was also a consequence of my studies of the Zariski cancellation problem. And these are now some more cases which have been taken care for n equal to 3 case. And so this was due to David Wright over a algebraically closed field, that if F is of this form where A and B are polynomials in X and Y, this was generalized to any field K by Prasenjit Das and Amartya Kumar Datta. And later Peter Russell and Avinash-Sathaye, they consider this any polynomial in 3 variables where A0, A1, An minus 1, they are polynomials in X and Y, with a condition that, so there is a condition that the GCD of this An minus 1 up to A1, so this is not a constant. So then if F defines a plane, F must be a coordinate. So a slightly different result is due to Kalima. He assumes if all the almost every fibers of G is a polynomial ring in 2 variables, then G must be a coordinate. And this problem is completely open in higher dimensions, and very special cases have been taken care. Maybe this is not an exhaustive list, but let me now move to another important problem. This is a linearization conjecture, and this was due to Kambayashi, and it was again in this context Asanuma had considered his ring in 1994. So the linearization conjecture asks whether every algebraic K star action on Kn is linearizable. That is, if you have a Z-graded structure on a polynomial ring, then you can always find a homogeneous set of coordinates. So this is the conjecture, and it was known to have an affirmative answer, maybe by Kambayashi himself, that yes, you can do it for n less than equal to 2. So the case n equal to 3 was highly non-trivial, and it has been the effort of many mathematicians, which had eventually led to this solution for the complex numbers in an affirmative case, and it was there generalized to Russell and Koras. They generalized it to a field of characteristic 0, and for positive characteristic, I discussed this Asanuma's ring. You have to think about the case m equal to 1. This is an open problem. For n equal to 4, this is again open if characteristic is 0. However, Asanuma, using this Asanuma's ring, he proved that this linearization conjecture does not have an affirmative answer if n is greater than equal to 4. And for n greater than equal to 5, over the real numbers also he constructed examples, but it is open over the complex numbers. And there are also results and problems on linearizability of the torus action for r greater than equal to 2. So I will not discuss this, but let me now talk about the difficulty in proving this case n equal to 3, this linearization conjecture. So this is related to a family of examples due to Russell and Koras. And one of this example was this ring A. So this ring A again is a linear polynomial in Y. And this is, suppose V is then affine variety defined by A. So the question is whether this ring A is a polynomial ring in 3 variables. So this was an open problem for some time. And the reason being was that this ring A had several properties similar to that of a polynomial ring in 3 variables. For instance, A is a smooth ring. It is a unique factorization domain with units being trivial. In fact, this ring A is can be embedded inside C3. And not only that, all vector bundles or the projective models over A are necessarily free. The affine variety V, this is diffeomorphic to the affine 3 space, and this logarithmic codori dimension is also minus infinity. Had this been a 2-dimensional ring, then these properties were sufficient to prove that this ring is a polynomial ring in 2 variables. But for here, A is a 3-dimensional, and they were not sufficient, and so this remained an open problem. If you prove that this ring A is a polynomial in 3 variables, it would have led to a counterexample to the linearization conjecture, which we have now seen that it's an affirmative answer, and also the Abhyankar-Sathaye's conjecture, because this conjecture which says that if F is a plane, then F must be a coordinate, because here, if I call this polynomial to be F, sorry, if this ring A is a polynomial ring in 3 variables, and small x denotes the image of capital X, then all the fibers of non-zero fibers, x minus lambda, they are affine in two space. However, if clearly this the fiber for x is equal to 0 is not a polynomial ring, therefore this x cannot be a coordinate for any lambda, and hence that would be a counterexample to the Affine-Ker-Sathaye's conjecture. In a remarkable paper, Makalimanov have discovered an invariant associated to any ring A, which we now call as Makalimanov invariant. He proved that the ring A, for this ring A, the Makalimanov invariant is the polynomial ring Cx, where small x is the image of capital X here. Hence, this ring A cannot be a polynomial ring in because it is a polynomial ring in 3 variables. This Makalimanov invariant would have been C. Subsequently, Kaliman and Makalimanov, they showed that none of this Russell-Koras-Russell threefolds are isomorphic to the affine 3 space. This eventually led to Russell and Koras discover their theorem that every C star action on the C3 is linearizable. Now, another important problem which is still open is this ring A a stably polynomial ring? Because if yes, then it is a counterexample to the cancellation problem of Zariski in characteristic 0 for n equal to 3. There are some properties which supports this problem is that, so this invariant of Makalimanov, it was computed for A1 and it was proved that this Makalimanov invariant of A1 is C by Dubulas, and in fact Dubulas and Fazal, they have recently proved that the variety V defined by A is actually A1 contractible. So there is I don't know, maybe it may be a counterexample to the cancellation problem. I really don't. So now we come to this Asanuma ring of this type, where this z to the power p square plus t plus t to the power sp. This is a non-trivial line, and after receiving my solution for the cancellation problem, this ring, Peter Russell had asked me, what if you replace this by any non-trivial line? Is your ring A still not a polynomial ring? And what about the Russell-Koras threefold? Both this ring, they are of the form x to the power y minus fxzt, and this eventually led me to consider this more general ring where over any arbitrary field k and with a more general polynomial fxzt. So I had studied this ring. So for now, let k be a field of any characteristic and b be a polynomial ring in 4 variables and g be a polynomial in this. The small f denotes the image of capital F of the projection x is equal to 0. Then if you consider this ring, but m is greater than equal to 1, strictly greater than 1, then we proved the equivalence of the following statements, that this ring A is a polynomial ring in 3 variables if and only if it's a polynomial ring over the subring Kx, where small x is the image of capital X in A. And if and only if this capital F, the image small f, is a variable in kzt, and if and only if this polynomial G is a coordinate in kxyzt, and which is same as saying that x and G is a coordinate along with x. So in fact, I have proved an equivalence of some 10 statements, and so yes, so and it has other consequences also, which further this ring was generalized in higher dimensions, and I considered this ring x1 to the power r1, xm to the power rm minus fzt. Then I showed that if f is a non-trivial line, if f is a line, then this ring A is a polynomial ring. This ring A is a stably polynomial ring. That is, after adjoining one more variable, it becomes a polynomial ring in 3 variables, m plus 3 variables. However, if f is a non-trivial line, then this ring A is a non-trivial A2 fibration, as well as this ring A is not a polynomial ring over K. So the point is that here K is a field of any characteristic, and if you start with a line, it is stably polynomial. If it is a non-trivial line, it is not a polynomial ring. And hence, you have a counterexample to the Zariski's cancellation problem for any dimension n greater than or equal to 3 over a field of positive characteristic. So here the positive characteristic comes into the picture, because such an example of non-trivial lines you can have only in the field of positive characteristic. I will discuss about this result more in this sectional workshop of ETH Zurich on 14th July. Now I come to this method of proof. So for that, let's have to introduce the exponential map on any ring A. So an exponential map phi is a ring homomorphism from A to a polynomial ring AU, which satisfies the following two properties. So these two properties are the two actions of the group actions. That is, this composition is so phi U, and this projection map, evaluation map that U goes to 0 is the identity. And this phi V composed phi U is phi V plus U. So these two actions are essentially the two actions of the group actions, which have been written algebraically. So for any exponential map phi on a ring A, the ring of phi invariants is denoted by A phi, is superfix phi, which consists of all those elements A which are fixed by phi. So it is a subring of A. For example, if I consider this exponential map from Kx on Kx defined by sending x to x plus u, then the exponential map phi is an exponential map, and this ring of invariant is clearly only the constants. An exponential map phi is said to be non-trivial if this ring of invariant is not the whole ring A, and the Derksen invariant of a ring A is a subring of A generated by all those A phi. So this invariant was discovered by Derksen, where so you look at the subring generated by A phi, where phi varies over all non-trivial exponential maps. So it is denoted by decay of A, and Kalima says that the Derksen invariant of the polynomial ring Kn must be the whole ring Kn if n is greater than 1. And the proof is very simple, that you consider two different exponential maps, phi I and phi j, where I not equal to j, and defined by phi I of xj to be xj plus delta ej of u. Then A of phi I is the ring of invariant is just xi being omitted. So if you have I not equal to j, then the subring generated by A phi I union A phi j must be the whole ring. So now I give a sketch of this proof, that why is this ring A is not a polynomial ring where m is greater than or equal to 2. So there is a proposition which I proved, that the Derksen invariant of this ring A is actually contained in the subring Kx_Zt. So that proves that A cannot be a polynomial ring, because if A is a polynomial ring, then Derksen invariant must be the whole ring. So this is the proof. So this is essentially the proof follows from this proposition. And now let me give you a bit of sketch of the proof. So the proof is that suppose the Derksen invariant is not contained in this subring Kx_Zt, then you can have a non-trivial exponential map for which the ring of invariant A phi is not contained in this subring, and hence you can define an filtration on a ring A such that phi induces a non-trivial exponential map A phi hat on the associated graded ring grade A, which is of this form. So all these things are a bit numerical, and a proof of which have been illustrated also in a book by S.N. Kreshola and Kuroda. So Kreshola had given an illustration of this proof, that y is true. So here this small y is in grade A of phi hat. And again, so suppose once you get this, you now define another filtration on grade A such that which will eventually lead to a contradiction. So essentially, means you keep on taking filtration and the associated filtering. Hence, this ring A is not a polynomial ring for m greater than equal to 2. So now I end my talk with this example of Professor Bhatwadekar and Amartya-Kumar-Dutta. So this is a polynomial ring in 4 variables, and R is a subring of A generated by T and F, where F is this linear polynomial in Z. So clearly it's a linear polynomial in Z with this coefficient of Z is T times X square. Then they have proved that this ring A is an A2 fibration over the subring R, and polynomial ring is after adjoining one more variable, it becomes a polynomial ring over R. And the fibers of F are all affine 3 space. So in fact, all the fibers of F are affine 3 space. And they raise this question whether A is a polynomial ring in 2 variables over R. Or at least, can you say that A is a polynomial ring over the subring CF? So his Professor S.M. Bhatwadekar, he and my supervisor, Professor Amartya-Kumar-Dutta. So Professor Bhatwadekar is a supervisor of Amartya-Kumar-Dutta and my grant supervisor, also my collaborator. And this is the school of algebraic commutative algebra built by students and grad students of Bhatwadekar, and along with, so is Professor Rodenberg, who had done some prolific work in the area of local exponential maps of local important derivations, which is a version of exponential map in characteristic 0. So this picture is taken in a conference which we have held in IIT Bombay. Now, the question is, which I leave it as an open problem, that whether A is a polynomial ring over R. And if you prove that the answer is no, then you have a counterexample to all the following problems. So the affine fibration problem over C2, or the cancellation problem, or the epimorphism problem. So this is the Bhatwadekar-Sathaye's conjecture. Thank you. So I finished my talk.
Thank you very much. That was beautiful. Coming from a little bit of an unknown, this isn't. I'm not an expert on this, so just asking, and you now prove that the cancellation problem for affine spaces is not correct in higher dimensions, as long as the characteristic is positive. And you're now listing all these theorems that would follow in characteristic 0 for the complex numbers. Do you have a feeling whether this should be true or not, now that you managed to find a counterexample in positive characteristic?
I really have no idea. It's a really difficult problem. Actually, this example of Bhatwadekar and Dutta, it was published in 1994 in an ICTP paper. It was also rediscovered in 2000 by Venedau, and commonly nowadays it is known as Venedau polynomials. And there have been several papers on this particular example, proving something or the other, supporting that the answer is yes, but still now there is no proof.
So when you say the answer is yes, you mean the cancellation problem is, cancellation holds, you mean, or?
It may be a possibility for n equal to 3, but then again, this Russell-Koras example is still lying there. Mm-hmm. So one doesn't know. As I said, this is one of the major difficulty, is to define this how to prove whether some ring is a polynomial ring. So that is one major difficulty. And the another major difficulty is how to prove whether a polynomial f is a coordinate. So this proving that A is a polynomial ring over R is same as asking that whether f is a coordinate. So proving that given any polynomial, whether it defines a coordinate, that's a difficulty of this area.
Right. Okay. Well, thank you very much. I don't think we have people online, unfortunately, but you're giving another talk in Zurich, you said, right?
Yes, yes.
This coming week. And so I hope there's an audience, a live audience there, and we will get lots of questions
Thank
So
you.
thank you.